Hello, my name is Justin Seibrant, and I'm working with the Storage System Group at NERSC under Jason Hick and Greg Butler. We're working on a way to move our large multi-petabyte file systems as quickly as possible. NERSC is the National Energy Research and Scientific Computing Center, and there they house Edison and Hopper. These are two large supercomputers that are used to cater to the scientific community. Scientists will run experiments on these computers and generate lots of data. So where's all this data going? It's being stored on our general parallel file systems. These are an IBM product that allow multiple computers all access to the same file set at the same time. As you see in this tiny picture, multiple computers can all manage the same file set. So maybe one computer is managing just the metadata and all the others are helping move files. And this would be referred to as a GPFS cluster. So we have many of these at NERSC, and they range from hundreds of gigabytes to multiple petabytes of data. So we have an issue right now at NERSC because we are moving locations from our Oakland facility up to the Lawrence Berkeley National Lab. We can't reliably put all of our hard drives on a truck and hope they don't break. Instead, what we're going to do is we're going to build a new system up on the hill and transfer all of our data over the network. That way we can make sure all the data actually gets there. The industry standard right now is to use these four tools to copy or synchronize your data. The first two are very familiar. The first is the Linux default copy utility. It uses one thread to copy a file byte by byte from source to destination. It's of course slow, but it's industry standard. rsync is a little smarter. It is able to determine the changes between the source and destination and sync only bytes that have been modified between the two files. Of course, it requires that you've had some form of a stale copy on the other end. MCP and Shift were both recently developed at NASA, so they haven't become familiar yet, but they're currently catching on large facilities like at NERSC. MCP is able to take a single file and parallelize it across multiple threads, and Shift is able to run multiple copies of MCP across many nodes. So both of these have large speed increases when we're dealing with huge file sets like the one at NERSC. So we've been developing a tool that would use these other tools in order to perform a larger file sync. So I've done some work determining which one of these tools would be best for our purposes. Here is a graph that shows how long it would take to copy individual files using each tool. And it ranges from a couple of kilobytes to a terabyte being the largest data point. And you can see that each tool scales linearly, and tools that are built for copying files, so not rsync, all the other ones, have a much lower slope simply because they're doing less overhead and are able to move these files very quickly. So looking at this graph, you might think that the problem of moving a petabyte of data might scale linearly and not be too big of a problem. Unfortunately, we also have millions and millions of files. This graph shows each of these tools copying empty files, so all they have to do is move the metadata of each file, but you can see that the amount of time it takes to do this job skyrockets after we cross a certain boundary. That boundary is defined by the stat cache, which is the GPFS cache to store file metadata. So that means that if a tool needs to work on 1,000 files, the GPFS will pretty easily get those 1,000 files into its cache and make accessing that metadata extremely quickly. When we have to copy more than 50,000 files, the stat cache is missed, and we have to go through and actually stat each file from the system. And you can see that on this chart, after we cross that 50,000 line, the amount of time it takes drastically jumps. Shift in particular needs to stat files a lot to coordinate between multiple programs all running on different machines. So it is the most affected by this number of cache misses. So we need some sort of new tool that's able to quickly split the work and do both copying and syncing, and it's going to use some of those tools that we just talked about. So disk sync is the tool that I've recently been working on, and it's able to determine the changes between two large file systems, and it's able to split the work of synchronizing them between multiple machines. And it's composed of three parts that I'm going to get to in a second. The first part is the job generator. Now, the job generator takes two file scans and processes them to determine the changes. So we use a GPFS utility called a policy scan, which can pull from the metadata a large dump of all the files. This is quicker than just traversing through the file system. And then we run some processing on that to get to a NERSC standard format, which lists all of the file attributes we care about in one line. These are sorted by path, and so you can take one from the up-to-date and one from the out-of-date system and run more or less a merge to determine which files occur in which system. If a file occurs in the new system but doesn't occur in the out-of-date system, then it's been added since the last backup, and it would end up in a file creation job. That's one of 7 different types of jobs that each describe some operation that needs to happen in order to get these 2 file systems synchronized. The job files are limited in size so that we stay underneath that file stack cache. Each job file will only get to 10,000 records within it, and no job file will exceed 1 terabyte in order to properly distribute this work. These jobs are then read in by the manager, whose job it is to sort the files and determine which order they should be run in. It then takes these job files and sends them to workers while making sure that certain requirements are met. For example, you can't create a file in a directory that doesn't exist yet, so it will make sure that all of the directories are created before the files are created. These workers are then sent off and they run independently and in parallel, and they take their job file in order to determine the work that they need to do. For example, this worker might have been given the job of copying 10,000 files, and it would take the information from that job and take data out of the up-to-date GPFS and move it into the out-of-date GPFS. This is how DiskSync is able to do a lot of work using these rather simple tools. Looking at some of the progress we've been able to make, we've run many tests on smaller file systems and are starting tests on file systems that actually do approach 1 petabyte. This test in particular was on 1 million dummy files with only about 100 gigabytes of actual data. This run tested DiskSync's ability to copy all of those files. So you can see in the beginning, it needs to create directories, that's the blue bar, on node number 1. And while node number 1's working on creating directories, none of the other nodes can work because we don't know if all the directories are there yet. Once node number 1 finishes creating directories, it lets the manager know that. The manager says it's okay to create files now and assigns creating file jobs to each node. From then on, we create files until the end of the run. You can see that there's one very long-running job on node 3 towards the middle. This is the job that's actually moving that 100 gigabytes. All the others are small, empty files that needed to be moved. This whole job runs in 31 minutes and 50 seconds. That accounts for the time that the job files were created and the scan files were processed, but it doesn't account for the creation of the scan files. We assume that these scan files are created daily in a routine backup like most facilities would be doing anyways. Because we can utilize these scans, we complete a lot faster than Shift, which moved the same amount of data in a much longer amount of time. Of course, there are configurations that could be made to Shift to make it faster. This was a more or less default case on both tools. A job that's more like a file synchronization was run after we had a set of data copied over. This example is a synchronization between 2 dummy file systems that contain approximately 4,000 changes on each, with the entire file system consisting of about 1 million files. This work was split into 120 jobs, and as you can see, many of them were file deletion jobs, which are able to run at the same time as some of these other longer running jobs. The directory creation and directory modification jobs take a long time, but while that's happening, we can be doing a lot of other things. And once we've removed all the files we need, we can start removing the directories that have now become empty, as well as creating new files. Just like in the previous run, where we wasted a little bit of time waiting for directories to be created, we do have a bit of an inefficiency at the end of this run. We have a long-running job that runs past all the others, and we see this area of unused time in nodes 1, 2, and 3 towards the end. This is a long tail, and it is definitely a current issue with our setup that long tails could drastically change the performance. For future work, we would very much like to be able to split this job mid-run and try to re-parallelize, but for now, this is an issue with our current system. We've started running on larger tests, on larger, more real data, and this test was moving 3 terabytes of changes and about 2,000 job files. Some of the long runners in the middle did have errors, which explains why we have these very three long-running copy jobs that don't contain much more data than the others. So other than the little bit of manual work getting some things unstuck with these longer jobs, we do see that most jobs complete very fast. The areas that appear black are simply areas where the jobs complete so quickly that the black borders around these squares pile up on each other. Current changes have been made since this run to stop these long-running or stuck jobs. Previously, we were using many copies of MCP, which was an over-parallelization. We tried to get more threads than were really on the system. Since then, we have switched to copy, which, although it is the slowest of the copy utilities, is a guaranteed use of only one thread. And we are currently syncing a 400 terabyte system, so around a half a petabyte, and it's been running for a few hours, moving a couple of terabytes every minute or so. So we're really looking forward to seeing how this performs in scale, but of course during the move we're limited in hardware. So looking forward, we're going to continue evaluating this tool for use at NERSC and for use on our extremely large data sets. And once this hardware gets properly installed in the new utility and we get a chance to play with our new network that's being created, we're going to try for even larger tests.